Hi, welcome to our group project for CS598, Deep Learning for Healthcare at UIUC. Our group project topic is on drug discovery, variational autoencoder techniques for molecule generation. My name is Dixon, and I'm joined by my team members, Andrew, John, and Megan. Our motivation for this project was to create drug-like and synthesizable molecules from a deep learning model. For our purposes in this project, we wanted to just create molecules that were valid, that were real molecules, and we did this testing against RDKit. Our baseline model was a character-based chemical VAE model, which we took from inspiration from the paper Automatic Chemical Design using a data-driven continuous representation of molecules. We actually used a repo from a group involved in that paper called Espero-Gruzic Group, and this was the model that we based our baseline model of. In addition to the baseline model, we took a look at improving the validity of molecules from the model generated. We took a look at KL cost annealing, which is tuning of a hyperparameter during the training process. We took a look at comparing a model including teacher forcing, which was the Moses implementation of VAE. And then we also took a look at the differences of different inputs, the main one being SMILES, which was for the baseline model, and then we compared it to a different input variation called SELFIES. Each of our team members will discuss these in detail, as well as the coding and the training process, as well as the development process. As for the baseline VAE architecture, which you can see in the diagram above, it's comprised of an encoder, which then creates a latent space, and then the decoder uses this latent space to recreate SMILES. From this, the SMILES generated from the decoder, we then compared these SMILES generated from the model to RDKit to see if they were valid or not. The loss function is based on the maximization of log likelihood of an input distribution given a latent distribution. For the data set that we used for training is something called Zinc15, which was sourced from the DeepChem Python library. The main data set that we used was 250K molecules of lead-like compounds. And you can see an example representation of a SMILE below, which is actually ibuprofen. We did use some subset at time during the creation process to see if the model is working, but it's 250K, which was used for the results that will be discussed later in the presentation. I'll now pass it off to Andrew, who will speak more about SMILES in detail.
All right, we'll just take a minute to describe the SMILES structure. SMILES is a language for representing the molecules as a string of characters. In this example, we can see that this molecule is composed of carbons and oxygens. The atomic symbols for carbon and oxygen are in the SMILES representation. There's hydrogen in this model as well, that's implied. There's also implied single bonds between all of the neighboring atoms. But if you want a different bond type, you can use an equal sign for double bonds and hashtags for triple bonds and so forth. Also in the structure, we have some branches. Branches are represented using parentheses. You just wrap the atoms involved in parentheses. And then finally, in this molecule, we have one cycle. A cycle is represented with a pair of numbers, and you just label the beginning atom and the ending atom that create the cycle in the graph. So this grammar is fairly simple, but we can see that machine learning models will still struggle to generate valid molecules using this syntax and grammar.
We'd like to discuss briefly the infrastructure that was used in order to make this project a success. So we leveraged Google Colab for a lot of our R&D work. And then when we wanted to really go into the analysis of our models, we went ahead and moved into Azure ML. So leveraging Azure ML, we were able to create what are referred to as experiments. Experiments were runs of our particular notebooks. Essentially, we were able to run those on a particular image that we were able to submit a given run to. And during that run within an experiment, we were able to change various model parameters, and then we were able to log them directly into Azure ML. During phase 2, we wanted to explore the impact of annealing on the KL divergence in our loss function. The loss function is broken into two components, the reconstruction loss and the regularization term. This term comes from the stochastic sampling of the normal Gaussian prior constructed from the mean and the variance of the variables in the latent space. In our baseline model, a weighted term is placed on the KL divergence, and that's initially set to 0, and it gradually increases so that early training focuses on the reconstruction loss and later focuses on the KL divergence loss. Our original model leveraged KL cost annealing, and in phase 2, we actually set that weight equal to 1, and we found degradation in our model's ability to generate valid molecules. This demonstrated the impact and the role that KL cost annealing had on our model's performance.
The next modification that we made to the model was to add teacher forcing. Initially, we attempted to modify the DeepChem library and implement teacher forcing ourselves. That proved a little bit too challenging, and we were able to then find another package that had already provided that teacher forcing as part of the variational autoencoder model. The motivation for teacher forcing is to improve the decoding process in the model. The decoder will decode one character in the sequence at a time. But if that character gets decoded incorrectly, then that incorrect result gets propagated throughout the rest of the model and messes up the results going forward. The strategy with teacher forcing is to give the decoder access to the full true sequence so that the decoder, when training, can make predictions and then propagate the true value forward to the next layers, so those layers are able to also train and not be as dependent on getting a correct input from the previous layer. This strategy and technique was able to significantly improve the percentage of valid molecules that our model was able to produce.
So SMILES-based latent spaces decode to mostly syntactically invalid strings, even with teacher forcing. And that's a huge problem because that's not very useful for drug discovery. So this has been addressed in multiple ways, but recently, the same as Puragusa group came back in March 2020 with a pretty elegant improvement over the SMILES language. So they came up with SELFIES, which is self-referencing embedded strings, and that provides a one-to-one mapping between SELFIES tokens and valid molecules. So unlike SMILES, every single permutation of SELFIES tokens translates to a valid molecule. And yet at the same time, SELFIES manages to capture and represent any molecule. So let's look at visualization of the SMILES latent space. Red is invalid molecules. Clearly, that's not very useful. So MDMA is an example, which is a drug-like molecule. SMILES string looks like this. SELFIES is maybe longer and a little less readable, but still pretty readable. And notice that the tokens are multiple characters, so we'll address that later. But say we introduce a random mutation to the SMILES string, it's almost always going to be syntactically invalid. Meanwhile, any mutation to SELFIES will always be valid. So in this case, the double one disappeared, still valid syntactically. So now let's look at what we actually did. So converting from SMILES to SELFIES is one thing. Then we need to single character tokenize, and that looks like this, just taking random Unicode characters to represent every discrete token, and it ends up looking like that. And then we pass that through the same character-based autoencoder. Didn't even have to change that model. So this is what it looks like, still training with the regularized continuous latent space and the reconstruction loss, and still using RDKit for validation once we do the pre and post processing to these different representations. So 100% validity always. That gives us the luxury of looking at other metrics of chemical richness. So QED, SAS, those are measures of drug likeness and synthesizability. Typically, you need to train a model to sort of predict that. So what is a little more useful is log-P and Lipinski's rule of phi, which are chemistry-specific domain metrics that can be hard-coded and used to evaluate some of this for chemical richness and usefulness for drug discovery. Comparison to similar methods, we have our grammar VAE that imposes some hard constraints on the autoencoder for syntactic validity, and the junction tree, which builds like a scaffolding outwards using chemically valid substructures that requires a bit of restriction on the sampling side.
All right, to wrap up, we'll just go through some of our results. We started off using the baseline variational autoencoder, and got up to about 3% valid molecules being generated. We saw a performance decrease according to our metrics when we disabled the KL annealing. Then we saw a significant improvement with the teacher forcing changes enabled. And then finally, this appeared to be a solved problem when using the SELFIES implementation versus SMILES grammar for the molecular representation. We were able to achieve 100% valid molecules as a result of the syntax, which is pretty cool. The caveat to these great results is that syntactic validity isn't the same as being synthesizable or usable in a lab, and that's a problem that's explored further, and a very interesting problem as well. Yeah, thanks for watching the presentation.